Hi there, welcome to Raylene Maths. In this video we will look at the standard form for a quadratic equation and use it to get the factorized form, the x-intercepts, and the turning point. First off, the y-intercept for number 5 occurs when x is equal to 0. When we substitute x equal to 0 in the quadratic equation, we end up getting y equals negative 15, which is the constant from the standard or expanded form. Next, in order to get the x-intercepts, we must factorize the quadratic expression. So we look for two factors that multiply together to give x squared, which are x times x, and also two factors that multiply to give negative 15. We need one positive and one negative factor. But we also need to see what the outer product and the inner product makes. We need to get a negative 2x. And the specific factors of 15 that we need here are negative 5 times positive 3. We then intersect this parabola, the same parabola as the expanded form, with the x-axis. The equation of the x-axis is y equal to 0. So when we substitute y equal to 0 in the blue equation, we get from factored form that the first x-intercept is going to be at 5, 0, and the second x-intercept will be at negative 3, 0. Remember that this sign change occurs from the zero product property when we solve the two individual linear equations or factors equal to 0. Because two factors multiply together to give 0 requires that either one or the other factor has to be 0. This solving results in the sign change that we see from the factored form of the quadratic equation to actually writing the x-intercepts as coordinates. Next, we can use those x-intercepts to come up with the axis of symmetry, which is a vertical line at the midpoint of the x-intercepts. So we add the two x-intercepts together and divide by 2. The midpoint, or the average of 5 and negative 3 then, is going to give us 2 over 2, which is equal to 1. And so we have that the x-coordinate of the axis of symmetry, and therefore the x-coordinate of the turning point, is located at 1. All we need to do now is take that x equal to 1 value and substitute it into either the expanded or factorized form to get the y-coordinate for the turning point. So I prefer using the factorized form, and I'm going to substitute into this blue equation to get the y-coordinate when x is equal to 1. So inside the brackets for the coordinates, I'm simply going to write 1 minus 5 times 1 plus 3. So my x-coordinate is still 1, and my y-coordinate simplifies to negative 4 multiplied by positive 4. And I can get from here that my turning point is at 1, negative 16. So there you have it, from the standard form to the factored form, getting all the information about the parabola so that you can then graph the parabola. The y-intercept, to recap, is at 0, negative 15. The x-intercepts are at negative 3, 0 or 5, 0. The equation of the axis of symmetry is x equal to 1, and the turning point is at 1, negative 16. Let's take a look at the next two examples. In number 6, we start off getting the y-intercept, noticing that when x is 0, the y-coordinate of the y-intercept is just the constant, positive 7. Then to get the x-intercepts, we need to factor the quadratic expression. X times x gives us the x squared, and then we need two factors to give us a positive 7. To get a positive number, we either need two negative factors or two positive factors. But because the sign of the middle term is negative, the two factors will be negative. 7 is a prime number, so the only factors for 7 are 1 times 7. Let's just expand this to see if this only possibility actually works to give us the answer we need. X squared minus 7x minus 1x plus 7 actually gives us the x squared minus 8x plus 7 we require. Now that we have the factored form, we can get the x-intercepts by changing the sign of the negative r1 and the negative r2. The first x-intercept will be located at positive 1, 0, and the second intercept at positive 7, 0. Once we have the two x-intercepts, we can write the equation for the axis of symmetry by finding the midpoint of the two x-intercept values. So x is equal to r1 plus r2 divided by 2. Just recall that the factored form with a equal to 1 is simply x minus r1 times x minus r2. And the r1 plus r2 divided by 2 gives us the x-coordinate for the axis of symmetry. The average of 1 and 7 then is 8 divided by 2, which is equal to 4. So now that we have the equation for the axis of symmetry, we can recall that the vertex or the turning point of the parabola is at the intersection of the parabola and the axis of symmetry. So x is equal to 4 at the turning point, and we can substitute that x coordinate either into the factored form for x or into the standard form for x. My preference is to use the factored form. So I'm going to substitute into the turning point coordinates immediately to get the y-coordinate. 4 minus 1 is 3, and 4 minus 7 is negative 3. So when we work this out, we can get the y-coordinate of the turning point. 3 times negative 3 gives us negative 9, and so we have a turning point at 4, negative 9. So to summarize, we have the y-intercept, the x-intercept, the axis of symmetry, which is an equation instead of coordinates, and the turning point. Let's take a look at number 7 now. We have the standard or expanded form, so we can immediately get the y-intercept as 0, 16. To get the x-intercept form, we need to factorize the quadratic expression x squared plus 8x plus 16. We know that the y-coordinate is equal to 0, and factorizing gives us x times x for the first product, for the first x squared, and then we need two numbers that multiply to give positive 16. They're either both negative or both positive. But because the middle term is a positive 8x, the two factors of 16 will both be positive as well. Now we have several factors for 16. We have 1 times 16, 2 times 8, and 4 times 4. And it turns out that the pair of factors we need here are 4 and 4. We can write x plus 4 multiplied by itself as x plus 4 quantities squared. And we will see that there is something special or different about this parabola because we can square the factor. We set y equal to 0 to get the x-intercepts. Writing this out in expanded form as x plus 4 times x plus 4 says, by the zero product property, that either the first factor equals 0 or the second factor equals 0. When we solve, this tells us that x equals negative 4 or negative 4. So we really only have one x-intercept, and it's located at negative 4, 0. The second point is really just the first point repeated. And now, to get the axis of symmetry, we find the average of the two x-intercept numbers. In other words, we add r1 plus r2, divide by 2. Here we can take r1 to be negative 4, and we can take r2 also to be negative 4. When we add these together, negative 4 plus negative 4, and then divide by 2, we end up getting negative 8 divided by 2, which is negative 4. So the axis of symmetry equation is x equal to negative 4, and we notice that the x-coordinate for the axis of symmetry and the x-coordinate for the x-intercept is the same number. Now to work out the turning point, we know the x-coordinate will be the same as the axis of symmetry number, and then we take that x-coordinate of negative 4 and substitute it either into the factored form for the quadratic equation, or we could substitute it into the expanded form. However, we notice that when x is equal to negative 4, we already have a corresponding y value, namely y is equal to 0 from the x-intercept. So let's just take our x-coordinate and substitute it into the equation. But let's put it into this simplified form, where we have the binomial squared. Substituting x equal to negative 4 gives us negative 4 plus 4 quantities squared. And then we get 0 squared, which is 0. So we end up getting a turning point at negative 4, 0. So to summarize our information, we have the y-intercept at 0, 16, one x-intercept at negative 4, 0, the axis of symmetry equation at x equals negative 4, and the turning point at negative 4, 0. So why do we have only one x-intercept? And why is that x-intercept the same as the turning point? The reason relates back to the fact that we could write this quadratic as a binomial x plus 4 squared. In other words, we had x plus 4 multiplied by itself. And that fact has to do with these numbers 8 and 16 and how they are related to 4. There's a pattern between the numbers 4 and 8 and 4 and 16. And once we understand that pattern, we will understand this special case of parabolas. Tune into the next video to see this pattern in action. Thanks for checking out Raylene Maths.